Ciao.
Ciao, see you later.
Ciao. Okay, so we start this next session on spin. There are again 6 presentations in this session. Each of these presentations will be 15 minutes plus 3 minutes of discussions. So I will give a warning at 12 minutes to each speaker. So, and I request everybody to kindly stick to the schedule. And the first speaker of this session is Yike Su. We'll talk on longitudinal and transverse spin transfer of lambda. Is the first speaker around?
Yes, can you hear me?
Yes, we can hear you and we can see your screen. So please start.
Okay. And this is Yike Su from Shandong University, and my presentation is longitudinal and transverse spin transfer of lambda and anti-lambda hyper in polarized PB collision at 200 JeV at RHIC-STAR. This is my outline. First about the motivation, then I will introduce the RHIC and STAR detectors. After that is the lambda and anti-lambda hyper selections. And then is the longitudinal spin transfer measurements and the transverse spin transfer measurements. And last is my summary. And it is the motivation. After many years, the knowledge about the proton spin structure has been obtained from the DIS and PP experiments. But the C-quark contribution to the proton spin, for example, the polarized distribution of the strange quark is still not well constrained by the experiment data. The plot on the right shows the longitudinal spin spin structure from the NNPDF. The left bottom's corner, it is the S-polarized distribution, and it has a larger uncertainty. And why we choose the lambda? Because the lambda contains a strange constituted quark, which is expected to carry the most of the lambda spin based on the model, the quark model, and the lambda polarization can be extracted from the angular distribution of the weak decay channel. Here we choose the lambda decay to the proton and the pion. In this formula, it is the angular distributions formula, and alpha is the decay parameter. And as for the theta star, it is the angle between the lambda polarization directions and the daughter proton momentum projections in the lambda raster frame. And from this, here I will introduce the spin transfer. And the first, the longitudinal spin transfer DLL in the PB collision can be provides a connection to the helicity distribution of the S quark in the proton and the polarized fragmentation functions. When the beam polarization is 100% polarized, the DLL can be written by the asymmetry of the cross section. And in the factorization, it includes the helicity distributions, partonic scattering, which can be calculated by the PQCD, and polarized fragmentation functions. And the plots here shows the predictions for the lambda polarization and the RHIC in the 500 JeV in the IPT with the dependence on pseudo rapidity. Here, the 3 models scenarios is based on the 3 assumptions on the polarized fragmentation functions. And when the beam polarization is changed from the longitudinal to the transverse, we can measure the DTT, and it is has a similar structure with the DLL. Here in the factorization, transversely distributions, partonic scattering, and polarized fragmentation function. And due to the transversity, its cherry-old nature, it is much less known by us. And this plot shows the prediction for the anti-lambda polarization with the dependence on the pseudo rapidity. And all the models a point is that the DTT should have a large value as the forward range. And the spin transfer has been already measured by at STAR using 2009 and 2012 data respectively. The previous measurements of DTT and DLLs shows on this plots. The left is the DLL versus Hyperon PT. Right is the DTT versus PT. The top panels for the positive pseudo-repeated range and bottom for the negative. As you can see here, the results are consistent with 0 within the uncertainties. So the measurement precision need to be further improved. And now the DTT have been measured at STAR using 2015 data at 200 GeV, which is as twice as large as the previous data set. And this slide shows the RHIC, and I think we already are familiar with that after this day's conference. So the only thing I will mention is the ring can be filled by the polarized beam. So we use the different bunch crossing can get these 4 spin patterns. And in 2015, we have more than 200 million events. And for the beam polarization, it is around 15 to 16 around this value. And this plot shows the STAR detector. For the DTT and DLL analysis, this falling sub-detector we used from outer to inner. It is the EMC, TOF, and the TPC. The TPC is our main detector to tracking and to do the particle identification. The TOF is used to improve the PID for the Hyperon dot track, and EMC includes the barrel EMC and indicate EMC, and it is used for triggering. And also we use the BBC and the VPD to monitor the luminosity, but it is not shown here. It should be in this range. And we select the hard scaling events by the jetpack trigger, which is based on the energy disposition in the EMC. As we mentioned, the proton and pion tracks appear to reconstruct the lambda and lambda candidates. After that, a series of topological cards are tuned to further reduce the backgrounds. This cartoon shows the topological card we used. And further, the sideband measure is used to estimate the residual background fraction, which is less than 10%. There is the 2 examples for the environmental distributions. And the spin transfer of the signal is obtained by the subtracting the contribution from residual backgrounds with DTT rho minus the DTT background contribution, and here the R is the background fractions. And for DLL, we use the same. We do the same thing. And then is the DLL measurements. DLL is attracted by a symmetry of lambda counts with the opposite beam polarization within the small intervals of cosine theta star. The cosine theta star is used average value, and n plus or minus, it is the lambda counts in the cosine theta star beam when the helicity of the polarized beam is positive or negative. R is the relative luminosity. And the plot here shows the example of the value for each cosine theta star beam in extraction. Top is the lambda, middles the anti-lambda, and bottom the K-short. The K-short was also reconstructed as the known check of our methods. And this extracted so-called Ning asymmetry. And here the alpha K-short is assumed to equal to 1. It is consistent with 0 as we expected. And this page is the new DLL preliminary results from STAR 2015 data. This plot shows the DLL versus PT for lambda and anti-lambda in PP collision at 200 Jeff. Red markers for the lambda and the blue markers for the anti-lambda. And the statistical uncertainty is still larger than the systematic uncertainty, and the results are consistent with zero within the uncertainties. And the theoretical curves are same with mission in the motivation. So the results could not distinguish among the difference of these model scenarios. And this page is the DL result comparison from this new preliminary results and the previous published results. The open markers for the previous published results and solid marker for the new preliminary results. The new DTT results are consistent with the previous, and the new DIL results is tended to the PT around 7 Jeff. Due to the twice large data size, it is have a factor of around square root of 2 improvement in statistical precision. And this part is for the DTT measurements. The first thing is how to determine lambda polarization directions. As shown in cartoons here, the direction of transverse polarization is rotates along the direction of the scattering plane. In the partonic scattering. The DTT is measuring the spin transfer to the final state polarization along the polarized direction of outgoing hard quark. And so we used jet anchors associated with the hyperon is used to obtain the polarization direction after the rotation. Then we used the anti-KT algorithm and with R equal to 0.6 to reconstruct the jet and require pursue rapidity of jet cars and PT cars. Then delta R is used to do the correlations with lambda candidates with and jet and require the delta R less than 0.6. And as for delta R, it is here. The DTT measurements is used another methods, and DTT is extracted from the cross-visual asymmetry using the lambda cones with opposite beam polarization within a small interval of cosine theta star. And this is the equation we use. And by this equation, here the relative luminosity and acceptance are both cancelled, which can help us to reduce the systematic uncertainties. And by this, and this measure was first used used in the previous star measurements in 2012 data DTT measurements. And this port is also shows the example for DTT extraction. It is DTT raw versus cosine theta star. Also top lambda, middles, anti-lambda, and the bottoms K-shots. And here the K-shots, so-called spin asymmetry is also consistent with 0. And this page is the new DTT results, preliminary results from STAR 2015 data. And it is the plots it also shows the DTT versus PT for lambda and anti-lambda in PP collision at 200 Jeff. The red markers for the lambda and blue for the anti-lambda. The top for the positive eta and the range and bottoms is the negative eta. So the conclusion is are similar with the DIL. It's also are small values with large uncertainty, and the theoretical curves are same with the we mentioned in the motivation. And the DTT, it is consistent with the model prediction, so which may indicate that the strange quark transverse distribution and or the polarized fragmentation function is small. Okay, this page shows the DTT result comparisons with published results, and it seems open markers for the published the data, and the solids are this new preliminary result. And the two results are consistent and compared with the published results. So you can see here it is these new measurements have a factor of around the square root of 2 improvement in statistical precisions. Okay, let's go to my summary. And the DL and DTT measurements in PP collision can provide access to polarized fragmentation functions and the strange quark helicity and transverse distribution in the proton. So new preliminary results of the DTT and DLL in the PP collision from start 2015 data with twice the statistical of the previous 2009 data and 2012 data, respectively. These new preliminary results are consistent with previous measurements and are still consistent with 0 within the uncertainty, which may indicate that the strange quark polarized distribution and or the polarized fragmentation function of lambda or anti-lambda is small. And in the future, STAR forward detector will upgrade in it is already updated, enabled to reach the lambda physics in the forward rapidity range. And because in the model predictions, it should have a large symmetry in the forward range, and more PP data will be collected at STAR in the 2022 and 2024. That's all my presentation. Thanks for the listening.
Thanks for a nice presentation. This talk is now open for questions.
Asmira, I cannot raise hand, but can I ask a question?
Please ask.
Thank you for the nice talk. Can you go to the slide 13 or 12? So you mentioned that your research, because of the uncertainty, not able to distinguish the different models, but you show here the model up to 2 GB or so, and your lowest PT being for the forward result, the PT around 1.5 or so. It may have some potential to distinguish your model if you have you tried to extend your model up to that lower PT region?
To lower PT range.
So you have a lowest point around between 1 and 2 GB.
Yeah, but the model prediction here is also very small values here. Although we could have a large statistic in the low PT range, but due to the detector's efficiency, we can't measure very low PT lambdas. So it is very hard. It is also hard work.
I see. So when you extend your the calculation to your lowest PT bin, you can measure. You couldn't distinguish still. There's no power for that. Is that what you're saying?
Yeah.
Okay.
Okay, thank you. Any further questions? Yeah, so why Bedford?
Yes, I have a question about the feed down. Do you hear me? The feed down from sigmas. Shouldn't you take this into account in your interpretation of the result? And is there any hope that you measure also the sigma 0? I mean,
sorry, I can't hear clearly.
Perhaps you can write in the chat box.
Okay.
Or you can even discuss in the chat box. Let us move to the next question, if you permit, Gunnar.
Yes, I was wondering about the longitudinal spin transfer. Here you plot versus PT, which I guess is the only scale now. It's a hard scale. Do you expect the DSE calculations to hold at the low PT? Or should one really consider on larger PT here?
Yes, in the large PT, it should have a more harder scattering. How to say? Yeah, which set the trigger? It is a jetpack trigger. It has the threshold that can help us to select this hard scattering, and
that's basically why the curves end at 2 GeV. Maybe that is basically where you start trusting perturbable calculation. Maybe the curves you plot the curves starting from 2 GeV, which I guess is when you start maybe trusting the perturbable calculation, and below that you are starting to become in a region where it's difficult to apply.
I realized that this theoretical curves it is used the same values with the previous published paper of the 2009 data measurements. So in that you can see here in the previous published data, we didn't measure in the low PT range, so we didn't draw the low PT the theoretic curves here. So here this new preliminary result is just to show the experiment results. So we didn't update the theory curves here.
Okay, we can probably go on, I think.
Move ahead. So I suggest kindly continue the discussion in the chat box, and let us thank the speaker once more, and we move to the next talk, which is by Umberto D'Alessio on lambda polarizing fragmentation function from Belle.
Thanks. So I'm trying to okay, this one. Okay, can you see and hear me?
Yes, we can also hear.
Okay, very good. So
if you can please make it full screen.
It's not full screen.
I don't think.
I think it is full screen.
It is. It is.
It is just a format. Maybe it's not completely.
Okay, that's fine. Please start.
Okay, thanks, Amit. Okay, maybe I can put even the webcam. Okay, so first of all, let me thank the organizer and the chair also for this opportunity to present these results. So these are based on recent work we actually last year we finalized it on the structure of lambda polarization from function, lambda polarizing fragmentation function from the Laplacian data. So first of all, I will try to, this is the outline of my talk. I will try to just sketch some idea about lambda polarization as a challenge and as a powerful tool. Then I will move to the TMD fragmentation function for spin-1 hadrons, and within the listed formulas, I will discuss also the plus and minus processes. And then the focus of my talk, the fit of Belle data and extraction of this polarizing fragmentation function, giving some prediction for PIC. So I look back, we know in the late 70s, and there were very important fixed target experiments are energy around 400 GeV for proton nuclei collisions, where they measure very striking result for the lambda producing exclusively in proton nuclei collisions. So the lambda was transversely polarized, or transversely with respect to production plane. And the main result is that it was very large, it's very large, and increasing with Feynman X And while for the anti-lambda, the lambda bar, there is no polarization observed. And if you try to compute this observable in collinear perturbative QCD at leading twist, you get very tiny results. So nothing to do with this very large value. So in '97 was a first formulation of TMD the distribution fragmentation functions, and in particular, I will focus on the polarized fragmentation functions, as I said, title of the talk. And that is the probability that the non-polarized quark fragments into a transversely polarized spin-1 alpha. So we performed the first attempt 20 years ago, trying to describe the data, and we got very reasonable results, but it was done in a phenomenological TMD model. And at the same time, there was an attempt in the twistor approach. But now we have new data in plus and minus process where we can really apply the TMD factorization. So a few words on the quark TMD's fragmentation function for spin-1 alpha hadrons. There is close analogy with the distribution sector. If you use the Listy formalism, you can relate the polarization of quark to the polarization of the final hadron to the Listy density matrix. These are the two Listy density matrices that carry the information on the polarization component of hadron, and here quark, in terms of this product of fragmentation amplitude that is a soft quantity. Just to give you an idea, if you sum over the diagonal helicity indices and integrate over the diffusion transformation, you get the ordinary collinear unpolarized fragmentation function. So this is a sort of the quark hadron population. If you include also the intrinsic transfer momentum, the same, you get 8 independent TMD fragmentation functions, similar to what happens in the distribution sector. If we put them in a table consider the polarization state on the horizontal axis and the quark polarization state on the vertical axis, we have the same structure as the distribution sector. In particular, along the diagonal curve, the diagonal part, you get the function that survives in the collinear limit, while in the corner, you have two very important functions. One is the Collins, the fragmentation function, left. The other one on the right is the polarizing fragmentation function. The main difference between these two functions, both are time reversal odd, but while the Collins fragmentation function is chiral odd, also the polarizing fragmentation function is chiral even, so you can access somehow easily or more easily. And they are both universal. Again, some history about that. I mean, the complete result for the azimuthal and polarization observable were derived already many years ago. Now we have also the proof of the factorization in terms of transfer momentum dependent fragmentation function for this kind of process. Now we are just performing the reformulation of the result by Daniel and Piet and Reiner in terms of the between the list formalism. Just this allows for a more direct interpretation in terms of partonic quantity. As I say, in the list formalism, you can compute the section for all kind of polarization for spin 1 particles in the final state by plugging the helicity density matrix. Here you see that you have the fragmentation function I defined before as the product of fragmentation amplitude and the helicity scattering amplitude that control the dynamics. Of course, since we are interested in a specific electronic observable, in terms of the hadron momenta, you have to proper convolve this quantity from the intrinsic transfer momenta
to the transverse momenta of the observed hadron in this standard reference frame that is called the hadron frame. If we now move to the focus, the spatial observable, the transverse lambda polarization that is defined as a single spin asymmetry. In the hadron frame, this can be measured and computed along n, that is the transverse direction with respect to the hadron plane. These are the two hadrons. And of course, if you work in the recipe formally, all quantities are defined in their helicity trains, then you have to project out. And for instance, the main quantity in this context is the polarization along the y direction. Y is the y in the helicity frame of the hadron 1, in such a case. And in this format, you get exactly two contributions. One driven by the polarizing fragmentation function, and one driven by the Collins fragmentation function for the other hadron. This is the hadron 2, but this is the hadron 1. This is the unpolarized fragmentation function for the hadron 2. But then if you integrate over phi 1, the azimuthal angle of the plane containing the hadron 1, also the other component, like the other transverse component, the x that I have not shown here, goes to 0. And more importantly, the Collins contribution also is vanished. So you are left with a polarizing fragmentation function. So you are directly sensitive to this quantity. We adopted for this analysis a factorized Gaussian model where we parameterize the unpolarized fragmentation function in terms of a Gaussian, and also the polarizing fragmentation function, terminal Gaussian, but times the power of the intrinsic transfer momentum, the quantity with the pole referred to the polarization width somehow. And if you apply in this this expression in the form derivation, you end up with this result. You can carry out all the integration analytically and compute the polarization along the n direction. And in such a case, you see that you have some factor coming from the Gaussian and the z-dependent part of the polarizing fragmentation function entering in the numerator of this expression. This, of course, integrator over the transverse momenta of the final hadron. We consider for H2 a light unpolarized hadron, but we include the mass effect for hadron 1. This is why we get this complex form. And we don't include any TMD evolution in such a case, since we are working a fixed scale. This is not relevant in this analysis. There is another process somehow related, and for which we have also data from their collaboration, that is the inclusive hadron production within a jet. This could be very useful from the phenomenological point of view, because you have a direct access to the intrinsic transfer momentum dependence. On the other hand, from the theory side, it's quite, not quite, but at least it's tricky. There is some issue concerning the TMD factorization, not the same as I discussed before for the double hadron, the two hadron case, the universality, and so on. So today, after my talk, you will hear quite a lot on these issues, and of course, there are a series of papers on this topic. Anyway, we use a simplified transfer momentum independent approach to deal also with this process. The main idea is just to check it for consistency with the two hadron case. There was also a paper by our chair and Mauro, Semino, and Ray Fisher, where they deal with the case within this simplified TMD model. In such a case, the polarization is measured orthogonal and this is computed orthogonal to the truss plane, and it get a very simple expression like this, where we have the complete intrinsic transfer momentum of the polarizing fragmentation. So now we move to the filter of Belle data. We perform a data selection because we have the data are given in Z, and there are some zeta being very large, including very large zeta value. So we exclude some of them, but we try to keep part of it. For instance, for the associated production, we just cut on the light hadron large zeta B. So in such a case, we get 96 data over 120. And for the lambda jet, we exclude the large ZBN of the lambda hyper. And now we are left with 24 data points. Concerning the parameterization, we use for the unpolarized fragmentation function two sets, one for the pi and and one for lambdas. For lambda, we don't have a fragmentation function set explicitly for lambda, but they are all for lambda plus lambda bar. So we have to separate the two. We check different choices and they don't affect our results. So at the end, we will use a very simple separation for the Q bar into lambda with respect to the Q into lambda. We have a Gaussian width for the unpolarized fragmentation function that is fixed value, while for the polarizing fragmentation function, we parameterize the Z-dependent part in terms of the unpolarized fragmentation function, and this ensures the fulfillment of the positivity part. How much time?
Currently, you have 1:30, 1 minute and 30 seconds.
So 1 minute and 30? Oh, so I have to rush. These are our results for the full data set. Chi-square around 2. We use the set of parameters to parameterize our polarizing fragmentation function. And you see that the up and down have a relative sign, and they should be different. If we restrict to the associated production data case, the chi-square improves quite well. A similar analysis was performed also by other people. So these are our results, where you see the description of the data. There are some tension for chaos. The chi-square for data points are reported here. For the full data set of only restrict to the hadron associated production. Okay. So we compute also the uncertainty band in the proper way. This is the description for the inclusive production case. Of course, in such a case, we don't have a very good description, but we have also to take into account that some features that are properly included in our theoretical approach is not clearly visible in the data, like the zero of the polarization at equal to 0. And okay, this is the first moment. There is a perfect consistency between the two extractions. So that means that even if we include the inclusive data, we don't spoil our. And these are some estimates for the semi-inclusive AS case for electron ion collider kinematics, where you see that the lambda polarization can be quite sizable and measurable. And this would be very important. So this is my conclusion. As I show, thanks to this data set, we are able to extract the polarizing fragmentation function. There is a clear separation in flavor with 3 different valence polarizing fragmentation function and some role for the C. And of course, the measurement and semi-inclusive DIS process could be very important, both for testing the universality of this function and to complement this analysis. Thanks.
Thanks, Umberto, for a very nice talk. And the talk is now open for questions. Yes, Gunnar.
Hi, Umberto. Nice to see you, and also nice to see the analysis. I had a question, maybe I missed it. On page 12, you mentioned that you exclude the high Z bin. What is the motivation for that? Because I would expect that at large Z you have a better sensitivity to the quark flavor because you have mainly favored fragmentation and not so much disfavored. Can you comment on that, please?
Yes, thanks very much. So the reason the following, you see, since this bin is very large, so it's not easy to compute, I mean, from theory point of view. On the other hand, we are approaching almost the exclusive region where also resummation contribution to play a role. So we check that also we included, we tried also including this, but we see that while, for instance, there are a combination of reasons to exclude these beings. One is from the theory side, and from the phenomenological point of view, we realize, for instance, the Chiron at large Z are not very well determined, and so that when we compare with the data, we get some higher chi-square contribution. For the inclusive lambda jet, we already know that we are entering into a very delicate region, in the sense that we are using our approach in such a way where maybe these effects are even more relevant, and even, you know, in our result, when we don't include this, but at the end we describe somehow the size but not the shape. There are some difficulties in including this data set.
Well, I would expect that actually most of the data comes from the lower region in that bin. Actually, it's 0.9, but of course, most of the hadrons are closer to 0.5 and not so much at the very high end of
yes,
that.
You're right.
But indeed, you still manage to describe the data even if you exclude it from the bin, from the fit.
Actually, we tried a different combination of parameters and also selection data, and this is somehow the best with the minimum set number of parameters.
Okay, thanks a lot.
Okay, Queen Wa.
Yes. Hi, Umberto. Nice talk.
Short question, please, and a short answer.
Yeah. Okay. So far, you don't include the scale dependence, right? Yeah. So, you know, at lab there are also some previous measurements at lab at the Z0 pole. The polarization there is also small. So, like we expect some like a scale dependence. At high scale, it will be the polarization somewhat smaller.
Cool. But maybe, as I said, we didn't use any scale dependence actually, because everything is obtained at fixed scale. It's not a global fit. If you try to perform a global fit, including data from different experiments at different scales, you have to be careful about this aspect. You're right. So at this stage, this is a sort of extraction of fixed scale. And then when we give the prediction also for kinematic for electron-ion collider, we use exactly the same value. So in such a case, there is no impact on the scale. But concerning what you say, yes, we should think about that and try to include it.
Yeah, thank you.
Anselm?
So may I have a comment about that, about the polarization at the lab?
You have a comment?
Yeah, I think in the learner talk, he will mention about that, about polarization at lambda polarization at the lab. And due to the statistic at the lab, it's not high enough, so they observe zero polarization. However, from a theory calculation, we found it's still non-zero. I think after my talk, Leonard will introduce.
Yeah, I was gonna make a comment, but I thought I would wait. Thank you, Dingyu. Yeah, so I will address this.
Okay, let us thank Umberto again. And
hey. Didn't you just call me for a comment? But
Okay.
Yeah, just
your comment is not ended.
No. 2 comments. One was what Qinghua already kind of.
Kindly make it short.
Hmm?
Kindly make it short.
So I just wanted to say 2 things. So one thing was Qinghua was already mentioning that the feed down is of course not in the results, not correct for that. So that's quite a big impact, and so we realized that you know, in general, theorists didn't kind of consider that, which is makes sense because it's difficult. But I just want to make that point. So any, like, you know, if you get a good agreement, it doesn't really necessarily mean that, you know, the physics that extract is actually correct, which is, of course, it's not your fault. We just have to do a better measurement there. And so the other comment I want to make is that we are working also on this measurement at JLab. So it would be, of course, it's going to be marginal, but it would be nice to have projections for that as well. Okay, thank you.
Thanks.
Okay, thank you for the comment. And now let us let us thank Umberto one more time. And we move to the next talk by Dingyu Shao on QCD resummation on single hadron transverse momentum distribution with the Thursdays.
Thank you. Let me try to share my screen.
Yes, yes, we can see your screen and you can start.
Can you see my slides?
They were here, but they have disappeared.
How about now?
Yeah.
Okay, good.
Yeah.
Thank you very much. Thanks, organizer, to give me this chance to introduce our recent work. So today I will give a talk about factorization and resummation on the single hadron transverse momentum distribution with the thrust axis at E plus E minus collider. And this talk is based on this work with Professor Zhongbo Kang from UCLA and his PhD student Fanyi Zhao. And as we know, the transverse momentum pattern distribution function and also the fragmentation function are the fundamental object to understand the inner structure of a hadron, and especially the 3D dimensional imaging of a hadron in the momentum space. For the TMD PDFs, there's a lot of progress has been made in understanding the 3D structure, where both unpolarized TMD PDF and also polarized TMD PDFs. On the other hand side, in comparison with the full result in the TMD PDFs, the research on the TMD fragmentation function need more developed. And in order to probe the TMD fragmentation functions, there are 3 main processes. One is the standard semi-inclusive DIS, and also dihadron back-to-back production at E plus minus collider, and also hadron inject measurement, which already mentioned in the previous talk. And besides these 2 processes, there's also some other measurement. For example, recently Belle collaboration report results for the inclusive hadron production, where at E plus E minus collider, they produce hadrons in the final state. At the first step, they define the thrust observable, and then they define the thrust axis as shown as this pink line, and then measure the hadron transverse momentum with respect to the thrust axis. In other words, as shown this black plane, it separates the full phase space into 2 hemispheres. In one hemisphere, you observe a hadron and measure the transverse momentum. On the other hemisphere is fully inclusive. Finally, Belle collaboration report this result, and this 3-dimensional differential distribution with respect to the hadron, energy fraction, transverse momentum, and also thrust. And in this page, I showed the result from Belle collaboration for this transverse momentum distribution with a different energy fraction range from 0.1 to 0.85, and also in the different thrust bin. Here, I only show the results when the thrust from 0.85 to 0.9. And for all pi plus, pi minus, k plus, k minus, and the protons result. In the small transverse momentum region, one can see very clear in Gaussian structure. And then the Belle collaboration and use a Gaussian formula to fit Gaussian width. And in this page, I show the results for the Gaussian width with respect to the energy fraction in this left-hand side plot for the pion, cation, and the proton. They observe very interesting result. With increasing of value of energy fraction, the Gaussian weight goes up, going up at first, and then going down in the large energy fraction region. So this is a result for the different hadron. In right-hand side, in this plot, they show the results in different thrust bin. And in each bin, you can see this interesting behavior. First it goes up and then goes down. Based on this result, there are already some phenomenological fitting work done by these two groups. They assume a function form and a Gaussian form to fit this such a distribution. And besides the phenomenological fitting work, and they also have some theory work. For example, Boglione and Simonelli and our group, we developed the TMD factorization formula for this observable. Besides the pure TMD factorization, and since we are interested in this dropping behavior, what happened in the large ZH region, then we developed the joint TMD and the threshold factorization formula. Besides that, since this observable exclusive with the thrust, so there also two groups developed the formula for the joint TMD and the joint thrust factorization. So in my talk, I will focus on first the two topics, pure TMD and the joint TMD and the threshold factorization. Of course, for the standard back-to-back dihedron, the TMD factorization formula is well known, almost well known 40 years ago. And at E plus and minus produce two hadron in the final state and then measure the relative transverse momentum. And then in the back-to-back limit, the cross-section can be factorized a product of hard function, TMD fragmentation, two TMD fragmentation function, and also a softer function. And we can look the famous Collins book to obtain the factorization formula. This is a typical two-scale observable. And then based on the factorization formula, one could factorize the TMD fragmentation function outside process, outside cross-section. So this is the well-known formula for the dihedron. However, our job is to understand the TMD factorization for the single hadron with the thrust axis. Before going to the full factorization formula, I will start from the next leading order structure. In this plot, I show this observable. For example, as I said before, the hemisphere perpendicular to the thrust axis separate the phase space in the two hemispheres. One is the left hemisphere, the other one is the right hemisphere. And in the left hemisphere, it's fully inclusive, it's unmeasured. And then in the right hemisphere, one measure hadron, and then especially measure the transverse momentum with respect to the thrust axis. When the transverse momentum much smaller than the scattering energy, this process in that limit will involve three different scales. One is a hard scale describing the energetic parton radiation in the left hemisphere, and also collinear kinematic mode describing the collinear radiation, and the softer mode describing the softer radiation. And both of them have the same virtuality. In right-hand side, I show this hyperbola plot in the light cone frame and the P plus component and the P minus component. We see this observable the cross-section involve contribution from hard part, softer part, and the collinear part. Based on this mode, and
I'm sorry, I think your slides aren't advancing. And maybe it's just my screen. I'm only seeing your Belle results.
Sorry, can you see?
Leonard, I have the same problem.
Okay.
Yeah, same problem for me.
Yeah, I think it is not advancing.
How about now?
Still see the Belle results, Dingyu.
Oh, what's wrong?
I don't know.
Let me try. Let me stop sharing and share again. How about now?
For me, it's still frozen on your Belle result slide.
if you can reduce the full screen, perhaps it will help. If you remove the screen mode.
Someone else can share the screen.
Okay.
Yeah, or we can do it from the Indigo.
Let me stop my video and see what happens. Let me share again. If it does not work, maybe you can help me. What's wrong? Can you see it now?
No.
No.
It's black screen.
Zhongning, can you share the screen for Dingyu?
And the screen be shared from
so I will share the screen for you. Is that okay?
Yes.
Okay, thank you. Let me stop sharing. Yeah. You have to go to page 6. Thank you.
Thank you.
There is no number. So,
Oh, you go to page next leading order analysis of TMD factorization form. Yeah, on this page. As I said before, when the transverse momentum of this hadron much smaller than the hard scale, this cross-section involves two typical scale, hard scale, collinear scale, and also softer scale. In the right-hand side plot, I give this hyperbola plot, and the softer radiation and the collinear radiation had the same virtuality. Based on this mode analysis, we can write down the factorized cross-section can be expressed as the last equation, and where we differential the cross-section as the energy fraction of hadron ZH and the transverse momentum. And then we can see it can be expressed as a product of hard TMD fragmentation function and the soft. And since both TMD and the soft have the same virtuality, both of them suffer from rapidity divergence, and also then it depends on rapidity scale nu here, I showed here explicitly. And compared to the standard dihadron factorization formula, we see there's an index on the hard function H, the index I, represent different flavor of parton in the right-hand side hemisphere. It can be quark, anti-quark, or gluon. And in the next page, please go, yeah, I will show the explicit next leading order expression for the hard function and also the soft function. For example, for the hard function, we can see the first diagram corresponds to virtual correction, which is similar to the standard dihadron case. And then there are also two other diagrams. The second one corresponds in the right-hand hemisphere, it's a quark, and in the left hemisphere, it's a fully inclusive, radiate hard gluon. And then the third diagram corresponds to gluon in the right-hand hemisphere. Then we calculate this contribution perturbatively, and as shown in the equation in the right-hand side, including different contribution. The first line is virtual, the second line is the second diagram, and the fourth line is the third diagram. And for the gluon part, we see at the next leading order is finite. There's no infrared divergence. So in order to verify the RG consistency at the next leading order, we only need first the two contribution. After combining them together, we found our hard function has a half of divergence of standard dihadron case. This is for the hard function. Besides the hard function, the soft function is also different from the standard case. The difference is that we only constrain the soft radiation in the right hemisphere. If the soft gluon is radiated in the left hemisphere, the momentum integral is a scaleless. So after explicit one-loop calculation, we see the divergence for the soft function is also half of the standard case. After combining them together, we can verify the RG consistency over all the divergence. The divergence of the UV divergence of low energy series cancel with IR divergence of high energy series. Also, the rapidity divergence will cancel out between this new soft function and the one TMD fragmentation function. In the next page is the full series. As I said before, this observable, if you go beyond the next leading order, you will see it involve a bit complicated structure since it's a so-called non-global observable. The one in the left hemisphere is fully inclusive, right hemisphere is exclusive. For this observable, the order structure does not have the simple exponentiation structure. And for example, at a leading log accuracy, one need to solve this nonlinear BMS equation. In our work, we construct we prove the factorization formula using the soft collinear effective field theory. Finally, we obtain this complicated structure, and this is all the factorization formula. And we applied the framework we developed 6 years ago. And a similar structure is also mentioned in the Boglione and Simononi's paper. And in the next page, based on the factorization formula, we could obtain the order resummation formula. Here, I show the resummation formula can be expressed as a first equation. And since it's a typical two-scale problem, one need after solve the renormalization equation, we could evolve the physics from high energy scale Q to the low energy scale, use the standard RG technique. And for example, for the evolution kernel, it involves linear part. And we found which is half of a standard dihedron case. Besides the linear part, it also involves the nonlinear part. This is for the evolution. The right part is contribution from non-perturbed correction. And we use the standard fitting result. We use the fitting result from the other standard TMD process. And then for the fermentation function, we use the DSS fermentation function for the collinear fermentation function. The next page is our numerical result. We found that they are consistent with the Belle measurement very well. This black dot are the Belle result, and the red band is our theory prediction. And we found the curve are consistent with the measurement. And this is in the low ZH range. If we want to understand the large ZH range, we have to also include the threshold resummation effect in the next page. So how much time do I still have?
-1.
Oh, -1. Oh, sorry about that. So, okay. So let me briefly introduce this part. It's we consider two limits. And when the energy fraction close to 1, and also at the same time, the transverse momentum much smaller than the scattering energy, we also using effective field theory to develop the factorization and also resummation formula. If you go to the next page, and also this is the resummation formula. In the next one is our result. Since, as I said before, this black dot is the measurement. They found the Gaussian width first goes up and then goes down. We found if we only use the standard TMD, the Gaussian width flows to a fixed value. And then we have to include this joint resummation effects as shown in this blue band in order to make a make a theory prediction for this result, for the result from Belle collaboration. Okay, in the next page, it's a summary. Maybe we can stop here.
Thank you, Dingyu. So questions, very short, maybe 1 or 2 questions. I don't see any hands, so perhaps you can ask the questions later in the chat box. And let us thank Dingyu one more time for this nice presentation. And we move to the next talk, which is by Leonard Gamberg on transverse lambda polarization in electron-positron collisions.
Okay, can you see my slides? Can you see my slides, Asmita?
Yes, we can see your slides.
Great. Okay, so thanks to the organizers for the opportunity to present this. Both Dingyu and Umberto did me a great favor, so I'll be able to go very quickly through the beginning of my slides. They've set up the theory and experiment phenomenology. So this is work that Dingyu mentioned also that doing with Dingyu, Zhangbo Kang, John Terry, and Fanny Zhao. And we have a paper on the archive. So here's an outline of my talk. Just motivation to study lambda, transverse lambda physics, as we know, is a long-standing challenge. I will go through a bit of the factorization that Dingyu went through, and also make some nuanced distinctions between the various results coming from Belle, and also propose the possibility that Belle can do an inclusive measurement just by switching from this thrust axis or back-to-back to the center mass frame, and then talk about the theory behind that measurement, and then I'll conclude. So I think you all know very well that a long time ago, this process was considered by Kane and Repko, and of course, QCD predicted that the result would be 0 for the polarization transverse lambda and E plus E minus. Clearly, and they also made a statement that observations of significant polarization and the above reactions would contradict either QCD or its applicability. Of course, we know there's been lots of progress. I summarized down here a little bit some of the work that was done to put this on much firmer foundation theoretically through TMD factorization. This is just a slide to mention the observable I'm going to be considering, which is the transverse polarization of lambda production in various processes, which is defined as the difference in the cross-section for polarization up and below the production plane. So what does experiment say? Again, Umberto covered some of this. There are many experiments, in particular older experiments of inclusive processes. There's also a nomad experiment of neutrino nucleon scattering, and then there's the Hermes quasi-real experiments that showed lambda polarization, and then I will focus a bit on the E plus E minus. So here's just flashing some slides from ancient measurements. You can see the polarization is enormous, 25%. The plot on the right shows a lot of the early Fermilab experiments and also a CERN experiment where the polarization persists in these various processes. Most of them were inclusive, PA to lambda X. It's even been studied at the LHC, but at mid-rapidity where the polarization appears to be about 0, but it does demonstrate the feasibility to study lambda polarization at high energy. So I'm going to focus on the E plus E minus, and one of the people today mentioned the data from Opal. There is data from Opal. Dingyu also mentioned it, that within the error bars for E plus E minus, this polarization asymmetry appears to be 0. Something that a bit I want to highlight is that this lowest point here should be at 0 because of just the nature of the mechanism for spin polarization. That is, if PT is 0, the cross-section should go to 0. So the question is whether there is some uncertainty offset or whether there's other processes involved, other factorization. So let me focus on the cleanest and very interesting results from Belle. They made 2 measurements. One was the thrust axis measurement and also back-to-back measurements. And I tried to illustrate them here in the right pictures. Both of them can be described from TMD physics because there is a small transverse momentum with respect to the large scale. And in the upper illustration, the JT is the lambda polarization transverse momentum with respect to the thrust axis that Dingyu talked about. And then if you talk about back-to-back, the red dotted line is supposed to represent 2 hadrons, and you're measuring the transverse momentum with respect to that. So here are the Belle measurements. The PT distribution is measured as a thrust axis variable, and you can see there's significant polarization. These slides are from Anselm's talk from last year. Here's the back-to-back measurements as a function of Z for various bins in Z lambda, so Z of the meson produced. So the question for global analysis and to test the universality is whether these 2 observables are measuring the same mechanism. And so let me say something about the mechanism. Also, Umberto did me a great favor on this, but I just want to emphasize that down here, in both of these cases, we have a relatively small transverse momentum compared to the hard scale. So you would think that these observables submit to TMD factorization. And this is just a slide to show the definition of thrust, which has already been discussed by Dingyu. The question for us is the same polarization fragmentation function in back-to-back hadron and hadron thrust measurements. And this, of course, is important to know, especially if you want to do global analysis. So the theory of this goes way back to the papers of Mulders and others, just in terms of a TMD framework. This polarization fragmentation function could be possibly describe an unsuppressed transverse single spin asymmetry. And of course, this is where it sits in the Young tableau, I call it. So this is the function that is both T-odd and chiral even that was mentioned by Umberto. And the factorization is on very firm foundation for back-to-back. BTOB means back-to-back measurement. We know, as Dingyu said, that this theorem goes way back to Collins and Soper. And on the right, I'm just illustrating the factorization in terms of the pieces of the factorization process. And of course, we all know from Collins's redo of the earlier work that the soft factor gets absorbed into the unsubtracted fragmentation function along with UV renormalization. And below here in blue, I just have the bare unsubtracted fragmentation function. This for the transverse polarization was also studied by Daniel Bohr, Zhangbo Kang, Werner Vogelsang, and Feng Yuan. And they showed that indeed they showed it was a universal function and it could be calculated in a kind of a quark target type model and look at the renormalization of this. And they made predictions of what the polarization would be for various experiments. So this is pretty much on firm foundation. Now the question is whether it's the same function that appears in both of these observables. As you know, Umberto presented the recent extraction of this function from the back-to-back and combining with the thrust axis data. So they're assuming it's the same factorization. Kang, Terry, and Callas also did it, but only with the back-to-back. And they these results, I'll say a little bit more about that. There's other very important phenomenological studies. Asmita and Mauro Anselmino, and I think Asmita's student, looked at single inclusive processes. And the question is, again, it brings up the issue whether it's the same polarization fragmentation function or should it be something else. And I'm hinting that there's a twist 3 function that maybe they were looking at. And also there's this earlier work that kind of set the stage for this by Mauro and others, Daniel Bohr, Francesca, and Umberto. Okay, so Dingyu saved me a lot of time. The question is whether this is the same function that appears in for a thrust axis process. Dingyu just gave a talk on this, and he showed how you can derive TMD factorization for a thrust axis observable. And I summarize here one of the interesting results is that when you write down the cross section, this is for unpolarized here, you have this soft function, it's called the hemisphere function, which talks about soft radiation on the side of the measurement. And they showed at next to leading order and next to leading log that the hemisphere function indeed was a square root of the standard soft function that is written down by Collins, which enabled them to write a renormalized ultraviolet and renormalized and rapidity subtracted finite TMD. And the factorization theorem is written down here in the bottom. There's also this extra factor here for the non-global logs that Dingyu discussed. So there is a factorization theorem for the unpolarized case. We extended that in this paper to the case for polarization. And a simple observation that because the polarization fragmentation function on the left here with the hat obeys the Collins-Soper equation, the whole object on the right satisfies Collins-Soper equation. So we have a factorization theorem, which I write in the middle of the page, which is the difference of the spin polarization up and down of the lambda. The only difference is that we have a Bessel function that's J1, and we also have these non-global logs. And the non-perturbative function, of course, is different, but the perturbative function is the same for the unpolarized case. So this is the factorization theorem that we're applying. So this is slightly different than using TMD factorization for back-to-back because of the non-global logs that Dingyu talked about. Okay, so let's talk about the phenomenology that we applied to this case. So this is a postage stamp of the input for our phenomenology to study the thrust axis data from Belle. If you would like to know a bit more about the non-global logs, you can stare at this and the non-global log term, and also the rest of it I think is pretty straightforward. We use this standard non-perturbative function that was used by Sun, Ixan, and Feng Yuan that we proposed back in 2014. And the parameters were fit from the Belle data by Callas, Kang, and Terry in the paper that that Umberto referred to. Anyway, so here was the extraction, here based on the extraction of the D1T perp that Callas, Kang, and Terry got from only using the back-to-back data. They came up with an expression for, a fit for the polarization fragmentation function. And here it is for various flavors, up, down, strange, and C. Then we exploited this to look at the thrust axis. And so here is our comparison of using, I should have put this on this page. We're using this evolution formula. I'll talk a little bit about the application of this both to Belle and to Opal, you'll see in a moment. So the input for us, of course, is this fragmentation function that they already extracted. So this is our description of the Belle data for the jet observable, for the thrust observable. The results are quite reasonable, and it's a proof of principle that the thrust axis factorization theorem applies to this. The error bars are pretty big, so the analysis of combining this thrust axis data with the earlier back-to-back data still makes a lot of sense, that as was performed by Umberto and company. Here is the Opal data and our evolution applied to describe it. Dingyu mentioned this. Again, I'm going to emphasize that the polarization is quite small, 0 within error bars. Again, this was more of a proof of principle that we can describe this data. The asymmetry is the polarization asymmetry is pretty small. But I want to highlight once again that the structure of this data, you would expect it to vanish at PT goes to 0, as our theory does. Now, the other interesting thing is that the data that Belle took that looks kind of inclusive, which is really not, its thrust axis. If you make a rotation to the center of mass frame, it turns out that the lambda with respect to the center of mass frame has a large PT. And this means that you could analyze this inclusively. So you measure with respect to the center of mass. Belle can probably do that. The question is whether, what does QCD predict? This is actually a twist 3 factorization, hard scale, 1 hard scale. So PT lambda is on the order of Q. And this is an illustration of the scattering plane and the production, and showing that this is a large PT with respect to the center of mass energy. So the question is, what factorization theorem should be used? Well, we wrote a paper a few years ago on how to study E plus E minus lambda transverse lambda polarization at next to leading order. And without going into gory detail here, there are 3 contributions that come into the cross section. There is the standard polarization fragmentation function, first moment of it, and then there's this twist 3 function dt. And we are able to use equations of motions and Lorentz invariant relations to re-express this entire cross-section in terms of this dt function. This function was written down by Daniel, Rainer Jakob, and Pete Molders back in 1997 in a TMD framework at twist 3. So they didn't use the twist 3 factorization. They came up with this expression, which we were able to derive using these relations. And so it's an interesting theoretical issue about what they wrote down back in 1997 and the factorization formula twist 3 that gives rise to the same cross-section subleading power. So here is the cross-section that one would use as prediction to analyze the Belle data in the center of mass frame. So what we did was, because we can re-express this first moment of the polarization fragmentation function through the equations of motion with respect to dt, we exploited this to make a prediction of what Belle would see. I can't go into all the details here, but we dropped this term, which is the interaction term in the twist 3 formalism, just to make an estimate. So we can see that we can, from the prediction of the polarization fragmentation function, we can make a plot of the this function dt.
Your time is up. Could you?
Okay, I'm done. So here's the prediction for Belle of the polarization, and question would be whether this is a feasible measurement for them. So here are the takeaways, that it's interesting that while these two measurements probe different distribution functions, they differ only by the definition of the measurement axis, that is dt and d1t perp. And the question would be whether this could be carried out at Belle. One last point is that if you, this function does not exist on the distribution side, if you try to turn this around, you'd get this function ft, which vanishes by time reversal. So the existence of this function and non-trivial result for the polarization asymmetry is a kind of a test of naive time reversal. So those are my comments, and sorry for going over. I'm done. Thank you.
Thank you, Leonard, for a very interesting presentation. This talk is open for questions.
Sorry, I should have shared.
Carlo.
Hi, Leonard. Very nice talk as usual.
Hi,
Thanks.
Carlo. Yes.
For your last predictions for Belle, you dropped that interaction term in the.
Yes. Yeah.
Okay. I mean, what are your expectations on that? And is there any other process from which you can get that term?
That's a very good question. In principle, yes, you could look at inclusive lambda production at the EIC. I didn't mention anything about this, but essentially we did this approximation based on pure ignorance that we don't know that function at all. Okay, so there are two unknowns in this business. I don't know if you can see the slide. Am I sharing?
No.
Okay,
no, but I mean, I remember.
Right. So. My point is that, you know, this is in principle another observable. You'd be able to maybe get access to this, but our approximation first was, can we just use what we know from the polarization fragmentation function d1t perp 1 and predict kind of on the order of magnitude what this thing would be. One of the ideas, we used this approximation in pp to pi x when we were studying RHIC data, and the argument would be that if that maybe this interaction term is somewhat small. We don't know, so it's just out of complete ignorance that we approximation.
No. Okay. I'm aware of that. It's just that
in principle, another observable. With another observable, we might be able to place limits on it. Yeah.
I don't know. Would be also maybe interesting to find a way to introduce a sort of systematic uncertainty on that.
Yeah.
Instead of dropping it right away. That maybe would be also helpful more for experimentalists, I think.
Yeah. We just to mention, we made a similar approximation when we were looking at the Collins function in inclusive proton-proton production at RHIC. So we don't know if that term is somewhat small. There's like a Collins, like, call it HFT.
Yeah, I remember.
Yeah, okay.
Okay, thank you very much.
Yes.
Any further questions? Okay, I had a question. So Leonard, if you express the cross-section in terms of the twist 3 function, will there be a suppression by a factor of Q?
Yeah, it's right here, Asmita. I went through that pretty quick. You can see, I don't know if, do you see my slide here? It says twist 3 pheno.
Yeah.
There's an 8m lambda over Q. So it is suppressed. And I think that you and Mauro and your student looked at data that would be submit to this more of this kind of factorization theorem, and it would be very interesting if you performed an analysis to put some constraint on this function as well. So you could maybe redo your analysis with this factorization theorem rather than d1t perp. If I'm not mistaken, you use the polarization fragmentation function.
Yes.
Am I right? Yeah.
Yes.
Anyway, so this is kind of an open and interesting issue from theory. And then, of course, if Belle can do this center of mass analysis, we'd maybe learn something about this function, which was actually written down back in 1997 by Daniel in his paper with Rainer Jakob and Pete Mulders.
Okay, thank you, Leonard, for a very nice talk.
Okay,
and
thank you.
let us move to the next presentation, which is by Anselm on measurements of inclusive cross sections and azimuthal asymmetries at light charged hadrons at Belle.
Okay, thank you. Let's see if there's some disaster when I try to share my screen. Okay, there we are. So usually something explodes when I go full screen, but maybe not this time. You can see it.
Yeah, please do.
Okay, good. I kind of suspect that I might be scheduled in the wrong session because this is not about lambdas, but in any case, as the title suggests, so this is discussing the recent update on the inclusive the measurement of cross-section and the update on the measurement of the Collins fermentation function. And it's based on these three PIDs that are here on the front slides. So since I gather from the talks and the questions previously that most people are, experts in this field anyway, so I can just go very quickly through my first slides. So as you know, that if you want to measure fermentation functions in particular for light mesons, a good place to do that is E plus E minus, where you basically produce quark anti-quark pairs in a usually back-to-back configuration, which allows you to access the fermentation functions without any other non-perturbative function in there. There are some, of course, drawbacks, most of all limited access to flavor, which you can do something about. In particular, you can use these back-to-back correlations that are shown here to get some limited information on the flavor, depending on the fermentation function. And then the other one is, of course, limited access to gluon fermentation function, which only comes in it doesn't come in at leading order. So if you want to do these measurements, as we also seen, most information nowadays comes from the B factories, and the reason is very simple. You basically have orders of magnitude more statistics than you have in other experiments. So every time I give these talks, over the last years, I show these slides about the inclusive cross-section of pion production at Belle, which is shown here in the middle in red. And obviously you see that the uncertainties are always magnitude better than anything that we had before. So in particular, because people, if they're here plus or minus, they often think about lab. You see that lab data is really insufficient to do anything where you want to measure more than one hadron. So because you basically run out of statistics at at high Z anyways, but even at lower Z, you barely have enough statistics to do cross sections. And so the experiments here of relevance are Belle, which I'm going to talk about, and there's also Baba, even though their fermentation function program, I think, kind of fell asleep by now, but Belle is still somewhat active. So Belle collected about 1 inverse attogram of statistics, and Baba roughly half of it, but for many measurements, we're actually systematics limited. So this difference in statistics doesn't really matter. So here, as I said, I talk about light mesons, pion kaons, mostly also a little bit of protons, but there are also other channels, D meson, fermentation function, lambdas, and so on. Okay, to give you an idea how the data looks like from Belle, so of course it's a B factory, so most of the data is taken on resonance, actually most on Y4S, but there are also other resonances that we look at. And there's around 10% data is off resonance, which is of course where you have this fermentation into light quarks, whereas on resonance the goal is to have B quark production. But fortunately, this B meson production makes only up a very small part of the cross section, as you see here in the cross section plots here. So only if you compare the peak, which was under the peak, you see that the majority of the events is in fact under the peak. And lucky for us, it's fairly easy to cut out this peak because these B meson events are fairly spherical because we sit right on the resonance. So by cutting on the thrust, this thrust event shape variable, which basically gives you, in some sense, like the two jettiness of the events. You can cut those out very easily. So you usually have this cut of thrust greater than 0.8, which then results in a small B contribution, smaller than 1% in the sample. So these things are actually not really a problem for us. So if you talk about contribution that you don't want, what's of more consequence are things like tau production and so on that contaminates our high Z sample, but B mesons usually are fairly benign. So how do these events then look like? As I said, the events that we select basically look like two jet events. So this is a plot of the event, here the energy flow in the event for this with this thrust cut that I just mentioned, and you see that basically we get a fairly nice back-to-back jet events. Okay. So this is kind of the introduction to the experiment and the data that we're using. So here's now the first results I want to discuss, namely the measurement of the cross sections of the light meson, so single mesons and also meson pairs. So as a kind of a background, I should mention that most of you probably know that cross sections have been measured by Belle already for various configurations. So the first measurement was way back in 2013, where we did the Z dependence of pion and kaons. So it's a PL in 2013. So it was extended to the dihadron cross sections. So basically combinations of pions, kaons, protons, and antiprotons. So it's a PRD in 2015. So then we added also the invariant mass dependence to that. So as you know, that's important if you want to use those to extract dihadron fragmentation functions, which are generally dependent on Z and the invariant mass, among other variables, but we focus here on Z invariant mass. So it was a presentation paper in 2017. And then the results that have been already discussed in this meeting here earlier in the session, we also looked at the single hadron cross-section differential with respect to the PT, with respect to the thrust axis. So that was a paper in 2019. So here, what I want to present is a paper from 2020 that I referenced in the beginning, which is not necessarily something exciting new, but nevertheless important to bring up. So namely, this is an update of the Z-dependent single dihadron cross-section. So there are two, or maybe like three updates which make this important if you want to use this data for fitting of fragmentation functions. The one is that we, as I explain in a second, we also include alternative Z definitions which have advantages for certain QCD analysis. But then these also include updated systematics and updated initial state radiation correction treatment, which I talk about a little bit in a second. So these updates have been, these kind of updated treatments have been kind of sequentially developed in some sense. So they are already used for these 2017-2019 paper. So this update basically mainly concerns the Z-dependent measurements that we did before that. So we only looked at the Z dependence for that. But of course, these are the results that are mostly used by fitters for the extraction of just integrated fragmentation functions of pions and kaons. So it's important to emphasize that these results, these old results, now have been superseded with these new results, and the differences are actually significant in some cases. Okay, so let me start with the first change, or the first addition is basically the inclusion of alternative definitions of the scaling variable Z. So originally, all our publication used this Z as just the fraction of the energy of the hadron compared with half of the center of mass energy. And so this, in some sense, relies, of course, on the, it's kind of assumes that you look at only the hadrons from one quark, and for which you can kind of determine, the energy of the quark by just using half the center of mass energy. So there are two alternative definitions that don't require this explicit hemisphere separation. And that makes them more well-defined at higher orders. So one is kind of the original one, the old one by Altarelli, Elias, Martinelli, and P, I guess. from the 70s. So it's an asymmetric definition of the Z The Z1 is kind of the same what we are using, whereas the Z2 is different. And as I said, it doesn't rely on the hemisphere, but the C2 will have larger values if it's a back-to-back configuration, and smaller values if they're both in the same hemisphere. So it allows a consistent analysis of kind of like integrated overall hadrons. And the other definition is a little bit newer, it's by Mulders and Van Hulst, Piet and Charlotte. And so the idea with this definition is, as we concentrate more on the transverse momentum dependence of these cross sections, so in particular we want to extract the QT dependence of the single hadron cross sections, it's important to define the Z consistently to our definition of QT. So QT is usually defined transverse to the large components of the form momentum of the hadrons. So if you then come up with a consistent definition of V, also including mass corrections, you come up with this rather complicated definition, but this is something that allows then consistent extraction also of the QT dependence. So that's what we included here. Okay, so this is an updated cross-section for light mesons, as I said. So it's a traditional, the traditional Z definition. So the main difference to the previous ones are the updated systematics and the updated ISR correction. It's just in some sense a reminder how things look. So it's in Z1, Z2 of the hadrons. I think that's not really a big surprise. So as you see, you know, pions, symmetries with pions are generally higher than with kaons and protons. And if you had low Z, the same charge and opposite charge, kind of the same cross sections. Whereas if you go to high Z, you basically see the effect that you have a quark anti-quark, so you have the opposite charges have a much higher cross section than the same charge. And the other thing is that I'm not sure if I can explain it like on the fly, but you see that the pi plus pi minus cross section does not necessarily drop at high Z as quickly as the other ones. So then we did a new ISR correction, and this is actually something important for anybody that uses these measurements. So this is shown in the same binning, so Z1, Z2, all hemispheres integrated. And so this is, so previously, I should say what we did previously, we did this kind of, yeah, so what we did is we basically removed events where more than 0.5% of the energy was lost in the intervention by ISR. So, and that actually was a relatively large correction, so only around 60% of the events were kept. So now we do something that might make a little bit more sense, or it's a little bit more you know, intuitively useful. So we basically do the ratio between with and without ISR. So we extract the ratio with different Monte Carlo tunes, and we basically apply this as the ISR correction and the systematic uncertainties, and basically the difference between the different tunes. So here the different lines are different tunes. The yellow is you know, basically the area between these tunes. And you see that we are now much closer to 1. So of course the ISR corrections rise quite a bit with Z, so particularly at high Z1, Z2, they reach you know 20-30%, but we are far away from these like you know 40% as before. So in general, the cross section that we report now actually grow quite a bit. Okay. Oh, well, okay, here's the next slide. It was always sort of stuck. So the other thing that we only have a new publication, but not for the older one, is the reporting of correlated and uncorrelated systematics, which is of course important for a fit of those. Okay, this didn't go. Okay. So the correlated systematics are usually from the variation of the Monte Carlo tunes, as you saw for this ISR corrections before. These are all correlated systematics. Things like acceptance and weak rate corrections we have uncorrelated comes from Monte Carlo statistics. And you see that as it in somehow way should be that the correlated systematics are you know the highest distribution contribution. No, otherwise we could just lower our systematics by increasing Monte Carlo statistics. So that's not the case. Only in the very high Z bands the statistic plays a role. And overall, as you see, we have systematics limited by several orders of magnitude. The red plot is here the relative statistical uncertainties. The same binning. Okay, so just so as a reminder, so this is an update to the single hadron cross section. It's the same thing as the PLL from 2013, just with the new ISR correction. The same story as before. So interestingly enough, so you have pion, kaon, and proton. you see the ordering to expect, and whereas at high Z, these pions and kaons get like closer to each other. I mean, there are probably several ways you can think about explaining that. One is like kind of, like favorite fragmentation dominates there. But the general two comments I want to make, so this cross-section is higher than before, reported before due to this different ISR correction, and it's definitely supersedes the old results. So finally, comparison of different Z definitions for inclusive pi, so same inclusive pi plus pi minus cross-section. You see this Altarelli et al. Is here it's A and P in blue and red, and then the one Pete and Charlotte's work in green and purple, and that these are the ratios to the standard definition that we used so far, and we see that there's kind of like this is integrated over both over the hemispheres. So if you separate by hemispheres, the difference of A and P becomes larger because just the way it's because it's asymmetric. But at least here you see that they are both generally kind of like smaller. So this A and P becomes the same as our old definition for high Z, whereas at high Z, this Mulder's Van Hulst kind of has the biggest discrepancy. So actually up to 50%, especially in these asymmetric events, which probably is because you get these larger QT values here. So these corrections probably play more of a role. So it's kind of like an interesting observation. Okay, I don't know how much time I have, but so
your time is up. Sorry, Anselm.
Okay, but okay, give me 30 seconds to remind you of our Collins results. So Belle has now added also PT dependence from Collins results, as shown here. Compared with Barbar, we see the same trends for unlike and ratio, unlike over like sign, unlike over all ratio. And we also have the pi 0 and eta, which is new, that doesn't exist from Barbar. So Belle is the only one. So we see this flat dependence in Z in PT for eta, and similar dependence for the T dependence. We did a test, an isospin test, to compare the pi 0 asymmetries with the unlike over like sign, unlike over charge integrated, which is if you do the fragmentation function decomposition should be the same. So we see so that all works out very nicely. So okay, so it brings me to my summary. So the hadronization program at Belle is still very active. I want to emphasize though that it starts also now at Belle 2. So we have now the first hadronization fragmentation analysis starting with the Belle 2 data, which start taking data 2019. So here I want to tell people that we're working on a SNOMOS white paper, QCD and hadronization at Belle 2. So if you have any, if you want to contribute or have any, ideas what we can do with Belle 2 data in terms of QCD and hadronization, please contact me. And then as for this talk, so as I said, we have these new Collins fragmentation function measurements. So please use them in your fits. So in particular, PT dependence is new, and the eta and the pi 0, and we updated the single and dihadron cross sections. Okay, thank you.
Thanks, Anselm, for a very nice presentations. Anybody has a question? Carlo.
Hi, Anselm. Very nice talk. Just a very quick question. Do you plan to release data for Collins asymmetry also in the, let's say for A0 instead of A12?
So for this analysis, not, just the way, so this was a student thesis, student is done, so this is not going to be touched anymore.
Okay.
Yeah, so, and when we did the analysis, so there were some problems in the A0 frame with, fake asymmetries, so we kind of ran with the other one.
Okay, thank you.
Thank you. Any other question? I don't see any other hands. So let us thank Anselm one more time. And we move to the last talk of this session, which is by Mariaelena. And she will talk about phenomenological extraction of a universal TMD fragmentation function. Hi.
Hello?
Yes, your slides are. Yeah.
Okay.
Please start.
Right. So it's a pleasure to be here today. I will present you some results that we have worked on together with Osvaldo Gonzalez and Andrea Simonelli. We had a very nice introductions by Umberto and Leonard and Anselm and also Dingyu. So I don't want to start too far away. The usual way we have started to learn about TMDs is based on 3 different processes. Drelian, which is polarized or unpolarized, CD scattering, and also a plus and minus annihilation into 2 hadrons. This is the usual historical way we have learned about TMDs. If we want to focus on fragmentation functions, Drelian is out of the game, and we have to rely either on CDs or on a plus and minus annihilations, which have been measured during the years in many different, very successful experiments. Now, in CDs, typically the cross-section is computed, is written as a convolution of a distribution function and a fragmentation function. I am writing here the expression into the conjugate space of BT, which is conjugate to KT, the transverse momentum, the transverse momentum involved in the process. And here is a schematic way in which we represent this pictorially, this cross-section. In this cross-section, you see that 2 different TMDs play an active role, and they are somehow related to QT, which, as I said, is the conjugate variable related to BT. The problem here is that the cross-section, so even the experimental measurement of the cross-section offers insight on the 3-dimensional picture of particles inside the hadron, which are embedded into the distribution function, TMD, and of the hadronization process, which is embedded into the fragmentation function. Unfortunately, though, these 2 important non-perturbative functions are convoluted, and somehow they make a tangle. And if you pull the line, the cord on both sides, the risk is that you tangle the rope even more. So one of the problems that we have been facing by doing phenomenology in the last few years is actually how to disentangle these 2 things. Now, one of the possibility, I'm stuck here. One of the possibility is to consider doing global fits. So simultaneous analysis of experimental data using different processes. For example, we know that fragmentation functions, TMD fragmentation functions, also appears in the E plus E minus cross-section, in this particular cross-section, E plus E minus annihilation into 2 hadrons, 2 detected hadrons. So again, the cross-section is a convolution of 2 different TMD fragmentation functions, one for hadron number 1 and one for hadron number 2. Again, we have 2 objects in the same cross-section, and which makes a tangle, and it's not easy to disentangle them. There is another process, though, which is cleanest with respect to the first 2 processes, which is E plus E minus annihilation into 1 hadron. If you write the cross-section for this particular process, you only have 1 fragmentation function appearing. So this looks very appealing, because finally you seem to be able to pull the cord, to pull the rope, and disentangle the tangle, because you only have 1 fragmentation function. But there is a but. And the problem is that this fragmentation function is not the same fragmentation function that you find in the previous 2 processes. So this is a very nice process, and we have wonderful data coming from Belle, very recent data with a fantastic statistics, which we would very much like to use, but we know that this fragmentation function is not the same as the fragmentation function that we have in E plus E minus into two hadrons or in CDs. Why is this TMD fragmentation function different from the others? Well, the reason is included in the soft gluon contributions. So, of course, inside these cross sections, we have a lot of soft gluons flying about, which are connecting the various parts of the partonic cross sections and of the TMDs. Now, traditionally, when we have been studying what we called a two-hadron class process, like CDs or double hadron production, so a process in which you have two hadrons going about, you define the fragmentation, the TMD fragmentation function, dividing in a very wise way all the soft contribution between the two functions. So basically, you define the TMD function by including half of the soft factor in one function, in one TMD, and half of the soft function in the other TMD, in the other TMD. So there is a sort of equal share of the soft contribution between the two functions. And this happens with distribution function and fragmentation function in CDs, and with fragmentation function number 1 and fragmentation function number 2 in E plus E minus. This is the typical definition of the TMD, which we usually call the square root definition, because you give a square root of the soft factor to one function and the square root of the soft factor to the other function, which is the definition that Collins has invented many, many years ago. For the E plus E minus into one hadron process, you cannot do this because you only have one TMD, okay? So you have to invent, you have to devise a way to actually write a factorized cross-section by managing somehow all this soft stuff, all this soft Bohr radiation that goes about. And this is the reason why whatever you do, since you only have one hadron, you don't know how to include half of or a square root of the soft factor into this TMD. So what Andrea and I have done in the last year, basically, was to invent a new way to define this particular fragmentation function in a way which was suitable for studying this process, but also in a way which allowed us to connect this new fragmentation function to the old one, so to the one that is used in the two hadron class processes, in such a way to ensure that all the work that we've been doing in the last 20 years was not wasted. So the way we do this is we give a new definition of our fragmentation function, which we call a factorization definition, which basically defines the fragmentation function as a purely collinear object. So all the soft contribution is all singled out, is all factored out of this definition, and is enclosed into a new function, which we call the soft function, the soft model. And this is basically embedding all the soft non-perturbative contribution of the TMD, okay? Now, if we multiply the soft contribution, our soft model, which for reasons that you well understand has got a square root, times the new purely collinear factorization definition, we find the old usual TMD fragmentation function defined with the square root definition. So everything is, on one side we have a new definition, but on the other side, we have everything under control, and we can go from one scheme to the other without losing any information. Now, having somehow settled this issue with the right amount and balance of inspiration and perspiration, you can actually factorize the E plus E minus into one hadron cross-section. And this factorization actually requires quite an amount of work, which I'm very grateful to Andrea because he basically did it all on its own. And you can factorize this cross-section, which, mind you, is differential in ZH, in thrust, and in PT, as a convolution of a pertonic cross-section with the new TMD. And this TMD crucially acquires a dependence on thrust. And if I have 2 minutes, I will try to explain you how this thrust dependence is acquired by the TMD. But the role of the thrust in this cross-section is fundamental, because here thrust is actually playing the role of a regulator. So you really need thrust in your cross-section, okay? Otherwise, you would not be able to keep under control all the rapidity divergences, for example, in this process. We work in a particular limit, which is consistent with the fact that thrust has to be very high, okay? T has to be as close to 1 as possible. This is the 2-jet limit. So basically what we require is that the PT, the KT of the partons inside the jet is very small, okay? So basically this is a pictorial representation of what we interpret as a 2-jet limit, so a high thrust limit, where here we have cleanly, this is one other special feature of this approach, of this scheme. We always, step by step, separate very neatly the perturbative from the non-perturbative part, okay? So this is only indicated in a pictorial way, but this is actually what we do in all our calculations, step by step by step. Now, taking the 2-jet limit has consequences on the scales which play a role in this cross-section. In particular, we have to introduce a cutoff for KT. So we say, to be in a 2-jet, quasi 2-jet configuration, KT has to be very small. So we, operatively, we require KT to be smaller than a certain cutoff lambda. But this is physically, from kinematics, is related to the value of T, or tau. Tau is defined like 1 minus T, okay? So basically, to go to the limit in which tau is very small, we also need lambda to be very small. And this is actually a sort of topology cut that we make on our phase space, which becomes a very small, a very reduced phase space, as you can see in this picture. Now, in 2 minutes, I cannot explain you all the details of this, but it's just to give you a flavor. So now, having done all of this, you can actually fix the scale by, as I said, by kinematics. This is a natural constraint given by kinematics, and you find out that the only way in which your subtraction mechanism is actually working properly is to fix the rapidity scale zeta to be equal to lambda square, and lambda square to be tau q square, okay? So you see that rapidity, lambda, the cutoff on KT, and tau are all related to each other. And these are physically observable relations. Now, once you've done that, your partonic cross-section, this contribution here in the actual total cross-section can be calculated. And as you see here, it acquires a crucial dependence on thrust, okay? Now we have one more ingredient, which is indeed our TMD. So when you factorize, after you gathered everything in your partonic cross-section, everything else is what you define as a TMD. And the TMD has the structure in this factorization scheme that you would expect. So it's got a perturbative part that we take at next to leading log order, and a non-perturbative part, which we have to somehow analyze through a phenomenological study. Okay, so in the perturbative part, we have the convolution of the Wilson coefficient with the collinear fragmentation functions, which for this particular phenomenological study, we choose to be the neural network fragmentation function 1.0. Although let me just make a quick detour here. We use these functions because they are particularly suitable for this phenomenological analysis, but because we will want to actually extend this study to see this as well, we are also keeping an eye and bringing forward our work of analysis using the Gen 20 fragmentation functions, which have been devised for CD studies as well. Okay, so convolution of the collinear fragmentation function with the Wilson coefficients. Here we have the Sudakov, basically the Sudakov part, or perturbative part of the TMD. And here we have the non-perturbative contribution, which is basically written in terms of two most important functions. The first one is the model MD, which in principle depends on Z and BT. Here, of course, this is a function which embeds the non-perturbative long-range behavior of the TMD fragmentation function. And in a minute, I will show you how we parameterize this. And then we have GK. GK is universal, is independent of the TMD definition. So it's the same for all fragmentation function and distribution functions. And this is an object that somehow we inherit from the factorization scheme that has been proposed historically. Here, I just want to point out that this GK function is multiplied by the log of tau, so thrust here, Q square over MH square. MH is the scale, it's a typical hadronic scale, and Q is the scale of the process. So
time is up. Could you kindly?
I'm done in a second. So somehow GK is related to the thrust dependence. Now we're all geared up for doing phenomenology. We are still studying the best parameterization to use for GK, because in a way this is relevant to get to the right thrust behavior. For the model, we have found that this phenomenological parameterization is the most suitable and the most flexible. Now, someone says, oh, this is very complicated. Actually, it's not complicated. We choose this parameterization because when you Fourier transform these into the KT space, you find something which is very closely reminiscent of a propagator. Okay, so it's a function which is properly normalized, and here is a picture of what we find in our phenomenology. Let me just stress the fact that this is very, very close to a Gaussian. So basically, this is a Gaussian, and the only different feature for this function is that the tail is dying a little bit less slowly. Okay, so that's the reason why we find it more appropriate for our study. But basically, in the overall shape is a Gaussian. It behaves like a Gaussian. Okay, so two very quick plots to show you our preliminary results. So this is what we find when we fit Belle data at a fixed value of thrust. Okay. So we fix thrust. The two shaded bins are not fitted. These are basically predicted. We put a cut in PT, which is proportional to Z times Q, with a factor which in this case is 0.2. We are still trying to modulate this to be the most appropriate possible. And as you see, the results are impressive. I mean, this formula that we have for the cross-section is actually reproducing the Z dependence of the Belle cross-section in an impressive way. We fit, in this particular fit, we have 89 data points and three free parameters. And no overall normalization, okay? So we don't need any normalization. We don't tamper with the normalization. As I said before, we also have crucially the T dependence in our cross-section, and we are actually starting to study how to reproduce and describe this T dependence of the data in the most suitable way. And this is just a taste that I give you for our study. Now, I'm done with my presentation. This is just an outlook of what we would like to do once we have finished our extraction of the fragmentation function in E plus E minus into one hadron. Then the plan clearly is to go to two hadron production. So as soon as Anselm will finish his analysis and will give us the Belle data for the unpolarized fragmentation function in H1, H2, we will be very happy, and we'll be happy to keep going with our analysis and in series, of course, with these schemes, which actually allows us to actually connect what we have done in this process to everything else that was done in the past. This is my conclusion, but you can actually read it yourself. Thank you for listening to me, and sorry for running over time.
Thank you, Mariaelena. It was a very nice presentation, and I see already one hand. Gunnar?
I think Sangling was first, but okay. Thanks, Mariaelena. I really liked your presentation. I'm still a little bit confused. You said that you can disentangle the TMD physics now. Does it mean if you fit, for instance, you have shown these slides earlier, that you fit one thrust bin, that if you only fit the data in one thrust bin, that you can predict the results for all the other thrust bins, because you have the fragmentation function, and you have basically the thrust behavior from the calculation?
Yes, that's
and
right.
You have tested this actually?
Yes, this is what I was trying to show you. We haven't finished this study actually.
Okay.
We have started. It's a little bit delicate. We're working. One of the difficulties here is that the data are in the KT space, but you work in the BT space, which is the Fourier conjugate.
Mm-hmm.
So
yes.
the little trick that we use is we focus on a few beams in the KT space. We focus on a few Z beams. We find the fit which reproduces them very, very, very well, so that we can trust that the lines are really going through the data, as you see here. Then we take these lines and Fourier transform them. And we trust that these will represent very neatly what the data would like in the BT space, okay? And then once we are in the BT space, we devise our non-perturbative models, okay? And we read out from the data, almost directly from the data, what the shape of the model should be. we have great fun in doing this, but it's a bit of a fiddling procedure, so it takes some time.
Yeah. So I understand correctly that here the left plot you fit, and then the right plot is extracted or computed using the
exactly. Exactly.
Okay, thanks.
Exactly.
Very nice.
Because the mass dependency is completely fixed by the formula.
Okay, thanks.
You're welcome. In a way, this is the difference between our scheme and what, for example, Dingyu has presented before. So we can actually predict the thrust dependence cleanly, purely.
Okay. I don't see any other hands. Any other question for Mariaelena? If not, let us thank Mariaelena one more time and all speakers of this session. And we close the session. And thanks to all of you for joining. There will be a break. And I guess there's another session after the break. So please come back.